I wanted to do this video because I don't think people realize how simple the mathematics is for encryption and key exchanges. And we are out because it's a well-lit day here in Bangalore. This is how your understanding will change during this video. Everything will be simple in the start, which will be followed by some confusion. But then we'll hit this minima. This is where your eyes will widen and smile will appear as things start to fall in place. We'll then build on this logic and the newfound intuition to reach a new place of understanding. The main aim of this video is not to teach workings of any specific algorithm, but rather lay the groundwork for you to start thinking about encryption as a whole. Even though we will be talking about Diffie-Hellman key exchange in quite some detail. Now the thing is that working with numbers like 1, 2 and 3 is much easier than working with alphabets like A, B and C. If we both know alphabets and we are on two mountain tops, it's much easier for me to flash my flashlight 3 times to mean C than it is trying to say C from half a kilometer away. Will it be slower? Sure, but the chances of mistake is next to none. You at least wouldn't mistake my C for an E. Computers face a similar problem. If we are using 5 volts as the operating voltage and divide it into 26 parts of each English alphabet, A is at 0 volt, B is at 0.2. Even a slight interference in the voltage will result in B being read as an A or C. We solve this by using binary. Everything above 2.5 is 1 and everything lower is 0. Then we resort to counting the numbers of these zeros and ones. This is what it means that working with counting numbers is easier than working with alphabets. Perhaps easier isn't the right word, it's more resilient. I made this one very simple website for us to play around with different mappings. And this is the simplest one, which maps 0 to A, 1 to B, 2 to C, and so on. And I have this one Unicode toggle mode. When we toggle that on, A is at 65, B is at 66, C is at 67. What's before 65, you ask? Special characters and then numbers, followed by some other useful things like space, and we'll see what not acknowledged. Now this is a Unicode table. It has letters from every single language, every emoji, everything. In fact, it's so robust that it even has all the chess pieces in all the 4 orientations. Now that we know how to share information, the question becomes how to share it securely. Unlike Unicode, which each computer has, encryption is only supposed to work between me sending the message and you receiving it. And that requires us to have a shared secret. This is Google Colab, and I used Gemini to write some very simple code for me. What it does is when I write some text, it just gives me each character's Unicode here. And down here, we have a secret number, in our case 124, and we multiply that with each one of these numbers and then convert them back to Unicode. Now for Namaste, that happens to be this text. If I send you this text, you really have no way of finding out what exactly do I have other than brute forcing it. Now some of you will recognize this as Caesar cipher. And yes, it's not a very complicated encryption algorithm. It's not very hard to break. You can brute force very easily through 124 numbers and you'll arrive at your number. But that's the key point. You'll have to brute force. Like if we choose very big numbers, then it becomes incredibly hard to brute force. The question then becomes, how do we arrive at the secret number? And this becomes spatially challenging with us on 2 mountain tops, with potential enemies always watching what we are communicating. The idea is, even with a public algorithm, there should be some loss of information, but it should retain enough that order doesn't matter. It can sound like a complex statement, but let's break it down. It has 2 parts to it. Say we take a number 47. One very simple operation we can do is to take the sum of its digits, in this case 11. Now if I give you 11, you don't really have a way to know what number I started with. It could be anything, 92, 83, 533. We have lost some information here. Another thing we can do is to take a remainder when divided by a given number, also called as taking a modulus. Say 47 divided by 5, which gives you the remainder 2. If I give you 2, you again have no way to find a number. It could be any multiple of 5 plus 2. Now that we know what loss of information is, 12 plus 10 is the same as 10 plus 12 is what we mean by order doesn't matter for addition. Great. Now, let's try to combine the two. What operation will lead to both loss of information and still preserve enough that order doesn't matter? Let's take the operation of summing the digits until the single digit is achieved. If I have two numbers, 32 and 98, if I apply the operation, we get 5 and 8. We can now add them and apply the operator again, 4. Or if we first add them, 130, and then do the operation, still 4. Similarly with modulus, If we take two numbers, 99 and 76, with a mod of 7, if we do 99 mod 7, which gives us 1, and then add 76 and take the mod again, giving us 0, it's the same as adding 99 and 76 first and then taking their mod. Some information is lost, but still order doesn't matter. Now let's use this to establish a shared number while we are on two separate mountains. Great. Now we have to first of all decide which algorithm to use. And say this is me, this is you, and you decide that let's just use mod with addition. You've just seen that it satisfies both our properties of order doesn't matter as well as losing some information, right? Starting here, where do we go? Well, first thing we need is which number to add to. Say you suggest the number, what, 355? So we both have 355. This we communicate between each other. Great. Now that we know that, I suggest let's also use one number for our mod. We need that. Let's just mod it with, and this is a space for your private number. So let's mod it with 17. I'll also mod it with 17. Great. Now let's choose our private number, right? Say I choose 89, and you just want to make sure that we are safe. You choose 100, no, 1973, right? 1973. So that's what you choose. Let's see what this computes to. So that is 355 plus 1973. Okay, mod 17. That gives us 16. So which color should we use? Let's use this. So this thing gives us 16, and the number which I had, which is the same but one number. I'm very lazy. It's with 89. We do this and I get 2. So I compute to 2. Great. Now what do? You give me your number, I give you mine. And then we do the same thing. So let's just do it. Let's just do it back here. Let's keep it there for reference. So what do we have? The numbers are, you give me 16, right? So I add 16 which you gave me plus with my private number, which is 89, and again modulus with 17. And what you do is you take my private number 2, you add it with yours 1973, and you do the same modulus with 17. Let's see what that computes to. So we have 16 plus 89 modulus 17. That gives us 3. This thing outputs 3. Let's see what this thing outputs. This is 2 plus 1973 modulus 17. And that also outputs 3. I mean, it has to, right? That's what it means, that the order doesn't matter. Let's just see what happened when we did any of these operations, right? Behind the scenes on all of them, the 16 is nothing but your private number, which let's just call it P1, plus the shared number which we have. It's just that. So essentially we are adding private number plus shared number with my private number, which is P2, modding with 17. This number is nothing but my private number, which is P2, adding with the shared secret, and this is your private number, P1. So essentially, overall, we are adding the same 3 numbers and taking the same mod. It's just that we haven't shared the exact information. Isn't that just beautiful that this even works? So what does our enemies get, right? In this case, say our enemies have a couple of numbers. They have 355, which was a shared number which we started with. Then this was our modulus, which is 17. Then they get my number, which is 2, and they also get your number, which is 16. Out of this, nowhere do they know 89 or 1973. They just have no idea about those. How can they though? Let's just try to form some sort of an equation if we can, right? So essentially, all that they know is, say, let's start with whatever you did. It's 355, right? Starting here, they know we added something to it, and taking modulus with 17 outputs 2 or 16. In this case, let's just take 16. Now the thing is, they really have no idea which number could it be. It could be any number, right? It like there's a infinite number of possibilities that this number can take. Okay, so let's just see how can they even start to thinking about it, right? Let's say they start by assuming, assuming that the shared number which you had was 0. What would they get? They'll get 355 addition with 0 modulus 17, which will give them 15, right? So this thing outputs 15. They were supposed to get 16, so they know that they're off by 1. All that they have to do is, this number is supposed to 1, and they'll arrive at this number. Fair? Let's just see if this checks out. So that will be 355 plus 1, that is 356, modulus 17, and that indeed gives us 16, right? So they have the number 1, which is a possibility. So in this case, our shared secret was 3. This thing we arrived at, nobody explicitly ever said 3, right? Now let's see how your enemies might react to this. They have, and at this point they are assuming the private number, your private number, to be 1, right? So they get 355 plus 1 modulus 17, which will give them a number, which is 356 modulus 17, which we just saw was 16, right? That's how they arrived at it. So they come to 16. Now they take this 16, they give it to me, they take my 2, right? This 2. So they take 2, and they now add it to the presumed secret number, and they do a modulus of 17, and they arrive at 3. The thing is, it doesn't matter if they have your private number or not. As long as they can find any one solution to the infinite number of solutions that there are, they can arrive at the same shared secret, and it's not very difficult to do. In addition, we can actually think of a very simple algorithm that we can run and find the first, like the simplest solution to the equation, right? Let's just see how can we actually do something which is a little bit more complicated. This time we have addition. Now sure, reversing it took a little bit more time. This time let's do repeated addition, right? So again, same thing. Let's start with a given number, 3, and we'll multiply it with our private number, P1. Okay, let's say our P1 is what, 5. We take a mod with 11. What do we get? 15 mod 11. That is supposed to be 4, isn't it? Yeah, 4. Okay, right. So this is the first number which you will be sharing, right? I'll be running through a similar number of mine. 3 is a shared number which we decided, which we agreed on. I choose my private number, which is P2. In this case, let's say that is 7. And we again take a mod with 11. So what do we get? 17, 21. The nearest is 22. So that would be 10. So I arrive at 10. I give you 10, you give me 4. And what do we get finally? I add 4 with my, I multiply 4 with my private number. 4, 7, 28 with 11, that will give me 6. You do the same. You take 10, which was my number, multiplied with 5, 50. The nearest we get is 44. So modulus with 11 still leaves you with 6, right? Of course, we still arrive at the same shared number. Now let's see how your enemies might see the same situation, right? So it's 3 times, what do we get? They don't know your private number, modulus 11, right? They have to guess. Let's try 0, doesn't work. Let's try 1, doesn't work. Let's try 2, doesn't work. Let's try 3, 9, doesn't work. Let's try 4, doesn't work. No, that's 1. Let's try 5, that does work. And in this case, that happens to be your private number, right? Now, as much as 5 works, so does 16. 16 times 3 mod 11 is also 4. Now that we have this, they could have used 5, which is in this case happens to be the smallest number. We should have chosen bigger numbers in this case. So what do we get is, like, we have 5, sure, but they could have used 16, ran through the entire number, and end up with the same shared secret. It happens to be the same thing, right? Any solution works. But did you see one very crucial thing? It was relatively easier to find the solution in the case of addition than it was in the case of multiplication. We had to practically brute force our way into 15, and I actually behind the scenes brute force till 16 to get to the number of the other private number which satisfies this equation. So this does make it look like reversing this multiplication is definitely harder than reversing addition. And that is very true. In this case, we right now don't, like, it's not obvious that we can think of a particular algorithm that we can use to find out the closest solution. Although there have been really smart people like Famart who have come up with solutions to this expression, and we can still solve it. It's very involved, but it works. And we do have an algorithm for that. But if we did not, like, a couple centuries ago, this would have been a perfectly valid solution. Given that if you would have used big enough numbers, it would be very difficult to brute force. And let's not use just numbers like 11. Let's use bigger numbers in this case. Let's use bigger private numbers, bigger shared numbers. It will become very, very difficult to find out which other numbers happen to fulfill the same solution. Now that I have said this, okay, I want to bring up one very interesting thing. And that is, we had, and like, I'm just going to ignore all mathematicians out there and create my own symbols. So this, for example, is say addition with modulus. And there are two things we are doing. We are going in this direction and then we are coming back, right? What we just did was multiplication with modulus. The same thing we did, going in that direction and coming back, right? Both of them were relatively simple. Let's just call this delta of difficulties. It's very small. It's very, very close to 0. But then this delta of difficulty here, it's a lot greater than what we had above here, right? So let's just follow the natural progression. This is addition and this is repeated addition, which is multiplication. The immediate next thing we can get to is repeated multiplication, also known as exponentiation, right? So let's do that. Say we have a base number 8, we raise it to a private number. Taking a modulus with 13 gives us, and in this case, say a private number is 20, right? 8 to the power of 20, of course I know what that number is. Modulus with 13 definitely gives a 1. Very confident, not at all. Never touch a calculator for this. So yeah, say we have this, right? What can we run with this number? Yeah, let's say this number is received by one of our enemies. What do they start with? They start with 1. 8 to the power of 1 doesn't work. 2 of 2, no, that doesn't work. 8 to the 3, no, that doesn't work. 8 to the power of 4, well, that does. You know what? Even 0 does. So if they were to use this, they could use both 4 and 0 or any other number to get to the same number, to get to the shared secret. But you know what? This is exactly the same that we have been doing so far. It's the same as addition, it's the same as multiplication. and so many solutions exist. But the craziest thing is, till date, we don't have one person who's able to come up with an algorithm to solve this. I mean, to solve the entire equation, and to find a solution of it. Wow. Okay, that went away. And this exact equation is what Diffie-Hellman uses for security. This one equation, some base to the power of a private number modulus some modulus is equal to some number which we then share across. This one equation is what is keeping us all secure online every single day. Why? Because we haven't been able to find an algorithm for this yet. One of the things which I see people is, they think when they are learning Diffie-Hellman in school or wherever they are, they think that there's only one possible solution, and it's very hard to find the private number. Yes, it's very hard to find the private number, but the question is not that we have to find the private number. The question is, any solution works as long as we have one. The challenge is that we don't even know how to find one solution to this equation. And yeah, there's a lot of wind here. So yes, this one simple mathematical equation is what is keeping us secure. And that just blows my mind. Now, once using this exponentiation with mod, we have arrived at a shared secret. We can use the shared secret to encrypt any message we have. Of course, do not use Caesar cipher because it will be hacked in no time. And the whole point of using exponentiation with mod will be just devastated. So just don't do that. But I think you can just see the idea of how we can use one shared number which nobody else knows to do some complicated things with it and try and encrypt a particular message. We'll talk about encryption in some other video, but in the meanwhile, why don't you take some liberty and go and try and figure out if you can think of one such encryption algorithm. Like, do you remember in the beginning of the video, we talked about how summing the digits until left with just one number also follows the same rules which we were applying? Yes, we can use that as well for encryption. Go ahead, try it out and see how prone, how secure is that algorithm. What is the difficulty of delta there? And what all other interesting ways can you find out to hack that system? When I was running through some numbers, it was fascinating what all things can you do when you are using, say, sum of digits, right? And if you're using with your friends, why not just go and play around with it? There are a total of 3 takeaways from this video. 1, some information should be lost. Secondly, yes, some information is lost, but it should still retain that order doesn't matter. And thirdly, there should be a high delta of difficulty of reversing the entire process. Once you have arrived at one such algorithm, you know that you have cracked a new form of key exchange there. And that's all that key exchange really has.